So let me say what the key thing is that I want to say, which is that there is a huge difference, I believe now, between if we consider that the universe is open or closed. Closed means it's spatially closed like the surface of the Earth, but in 3 dimensions. Open, that it's infinite. And I think that there is... this difference is hidden in general relativity. It doesn't look so great in general relativity, but I believe that it is absolutely huge, and I want to explain why that is. So I'm going to start off by going back to the foundations of dynamics and some very fundamental questions that came up then. But first of all, I want to say something about space and the role of space in the way we think about the world. Leibniz said in his argument with Newton said that space is real. Every point of space exists like a grain of sand. They're all identical to each other. Leibniz said this is nonsense, and he said that space is the order of coexisting things. And by the order, when he was pressed by Newton in the Leibniz-Clark correspondence, he said that order is the distance between objects, the separations between them. The only real thing are the separations between the objects. Now, I think Leibniz was halfway to the right answer. I would change Leibniz's statement to say that space is the order of coexisting facts. Let's go back to when the Egyptians discovered Pythagoras' theorem. It came out of surveying of the land surface of Egypt. Geometry means measurement of Earth. And suppose we have n points fixed in 3-dimensional space. They're not moving relative to each other. And we measure the separations between them with measuring rods, which nature in her bounty gives lots of them to us. And we measure the distances between those n points. We get essentially n squared separations. It's precisely n into n minus 1 divided by 2, but it's of order n squared. Those are positive numbers. They could be completely arbitrary. But a mathematician looking at them long enough would say, ha! These are actually the separations between n points in 3-dimensional Euclidean space. And the mathematician can say that because there are very precise mathematical relations that these distances, these positive numbers, satisfy. And out of this, a vast amount of modern mathematics comes already. You have the possibility of representing those points as vectors in Euclidean space. You have Cartesian coordinates. You have the similarity group of Euclidean geometry, translations, rotations, and dilatations, which take you from one representation of these points to another. This is an extraordinary thing, and that is the order of coexisting facts. That is a fact. My hands are of equal length. And it's the order of those lengths that underlies everything. So I think this is very important. So now let me go straight on to what I think is very significant now is, you've been looking at this picture for a while, I'll explain what I mean by this. Here is a triangle in Euclidean space. According to Newton, you need 10 numbers to say what's going on in Newtonian dynamics. You need the position of the centre of mass, 3 coordinates, the orientation in space, 3 more numbers. You need the 3 sides of the triangle, 3 more, and you need the instant of time. That's 10 numbers. Now the Leibnizian viewpoint really should whittle that down to 2. If this were the whole universe, and not in the environment, not in the context of Krakow, it would be just 2 dimensionless numbers, 2 angles that determine the shape of the triangle. That is intrinsic. The size of the triangle by itself, if it's the whole universe, has no meaning whatsoever. It's a dimensional number and cannot have any objective meaning. Its position in space is completely meaningless. Its orientation is meaningless. So this is what counts, and it determines the shape. I would say that the key concept that explains everything really that we can understand about the universe ultimately derives from shapes. Shapes are dimensionless. So that's the key thing. So that's an important point. And this is, I think, the right way to represent things here, that this is a principal fibre bundle. I'm not going to go into all the wonderful mathematics of principal fibre bundles. But the base space here is, it's going to be the way you should think about a universe of three particles. Each point in the base space is a shape of a triangle. Then these fibres up there are all different ways in which you can imagine that triangle represented in Euclidean space, position, orientation and size. And those are all identical as you go up and down the fibre. On the left here we have the group, the structure group. This is the similarity group of Euclidean space, which enables you, the generators of its Lie algebra, take you up and down that fibre, which is a 7-dimensional space, to different possible ways of imagining this thing embedded in space. But the reality is just the shape of the triangle. There is nothing more but that. These are all just ways of conceiving it. And then this is what the mathematicians call vertical motions, and they are pure gauge. There's nothing of physics in that if this is the entire universe. It's a totally different matter when I'm talking about this triangle here in Krakow here. Is that pronunciation reasonably good? Anyway, the real thing is when you go to a different shape, a different triangle, this triangle is incongruent to this one. They are different. And the fundamental question is, how do you define the difference between those two shapes? What is the measure of that difference? That is the key question. So, let me now go and point out that Newton promised to solve a very fundamental problem and didn't do it. In the famous scholium at the start of the Principia, he recognizes that there's something very problematic about his notions of absolute space and time, because they are not visible. And he recognizes as an absolutely key problem how to determine the absolute true motions from the observed relative positions and motions. And he says this is not an easy problem, but he suggests that it can be done, and he says how it shall be done in the treatise that now follows. For to that end it was that I composed it. And the remarkable thing is, he never returns to that problem. And virtually no one in the history of science has returned to it seriously. People were very worried about it, but not even Einstein addressed that question seriously. He created general relativity indirectly with great brilliance, a combination of opportunism, brilliant adaptation, generalization of Maxwell's ideas, all sorts of things. But Einstein did not address those questions directly. And this is what I'm going to suggest, that when you think about an infinite universe or a closed universe, things look very, very different. So that's what I want to come to. Now let me say what is the scholium problem. If today you open a book on textbooks of dynamics, it will introduce the concept of an inertial frame of reference. And it will say an inertial frame of reference is one in which Newton's laws hold. That, of course, is a truism, really. It doesn't address the really key question, is how do you actually determine the inertial frame of reference from what is observable? Let me say that the teaching of dynamics at universities is deplorable. You open any book on textbooks, they will not tell you how to determine inertial frame of reference. They talk about time and clocks, but they will not tell you what time is, and they will not tell you what a clock is. And when you're taught dynamics at university or high school, you start with Newtonian kinematics, which corrupts your brain because you think absolute space is there. Then you go on to Newton's laws. Then you solve the two-body problem, and then you jump straight to rigid body theory, and then you go to Lagrangian dynamics. All very beautiful. But the real dynamics actually begins with the three-body problem, which gave Newton a headache, so he gave up on it. So actually nobody who studies dynamics leaves university knowing really what it's all about and where all the problems are. It all sits in the n-body problem, and it starts with the three-body problem. And I know some of the world's leading experts in the three-body problem, and they say to me, actually, after 300 years of studying it, we still know essentially very, very little, next to nothing about it. So now we go on to the real issue now is what information, given observable information, how much do you need to determine an inertial frame of reference? And I'm going to pick up here from what Poincaré did in an analysis in 1902 in his Science and Hypothesis. I'm going to take it a little bit further. Suppose I'm given the shapes of my two triangles and nothing more, because that is actually all that's really observable and objective. These are different. Is that sufficient for me to determine the inertial frame of reference in which the Newtonian evolution is taking place that takes me from one triangle to another? Because Laplacian determinism, about which we've already heard quite a bit, only works in an inertial frame of reference. Poincaré said there's been a lot of discussion about absolute or relative motion. What precise defect, if any, arises because Newton describes motion in absolute space? And he identifies a very precise defect. He says, I am a convinced relativist. I believe that only relative motions count, and it must be, therefore, the case that if I know the initial... I'm going to go a little bit further than Poincaré and put it in my terms. If I know the initial shape of my triangle and the rate at which the shape is changing, so I'm going from one shape to another, if I believe that that is everything that counts, I should be able to predict the future uniquely on the basis of that information, just those two shapes and nothing else. And I put this question to Nobel Prize winners and so forth and say, is this true or not? And they've never thought of asking that question. They do not begin to know how to answer it. But it's actually very simple. The answer is you cannot predict the future on the basis of that information. You miss exactly 4 vital bits of information. The first is that those two triangles, in Newtonian terms, contain no information about the angular momentum that is in the system. I can change the angular momentum at will by holding them in different positions like that. I cannot predict, therefore, and now the angular momentum is absolutely crucial in how a system evolves, including how the shapes evolve. So I cannot, given those two shapes, which are incongruent, say how the shapes will go on in the future. I'm missing 3 bits of information. And there's one more bit of information which I'm lacking, which is that I don't know, in Newtonian terms, how much there is in overall expansion, how much kinetic energy there is in overall expansion. That's a 4th thing. So there is a 4-fold indeterminacy in the future evolution. And therefore, that is the precise defect of Newtonian mechanics, that 4-fold discrepancy. And it exactly goes back to those generators of the 4 generators of the Euclidean, the similarity group. The centre of mass motion doesn't count because doesn't come into the problem, doesn't affect this issue because of Galilean relativity. But the 3 of rotation and the 1 of dilatation comes in vitally. So now, what is actually and of course, the great thing about Poincaré is that he made Machs' ideas precise. Mach was very powerful in saying there must be something wrong with Newtonian mechanics, both as regards the definition of position and time, but he didn't give a precise criterion. That is what we get from Poincaré. And I will take poison on the following, that there is one correct, for a closed, dynamically closed universe, there is one correct formulation of Mach's principle, which is here. It comes in 2 forms. There is the strong Mach-Poincaré principle, as I call it. A point and a direction in shape space should determine the evolution of the shapes uniquely. That's the strongest form that one could require. And then there's the weaker form, which requires one parameter more to be specified. A point and a tangent vector in shape space determine the evolution uniquely. So that's what is the requirement. So let me say how that's going to be implemented. We've got this picture again here. I will be able to implement the strong Machs principle, Mach Poincare principle, if I can define a metric on shape space. By the way, let me just say that shape space is a completely general concept. All that is underlying this whole picture here is a Lie group. All I need to do this is a Lie group, either finite dimensional or its generalization to the three-dimensional diffeomorphism group or the conformal group in 3 dimensions, which I'll come to if time allows. So this is a completely universal way of attacking the problem. What I want to be able to do is define a geodesic on shape space, on my space of possible shapes. If I've got that, then a point and a direction in shape space will determine even evolution uniquely, because I can say the evolution is a geodesic on the shape space. And if you have a geodesic principle, it's a point and a direction that does it. So that's the thing. So you need to define a metric on shape space, and you're away. You're done. And there's a very simple way to do it, which is suggested exactly by the very problem that I started off with telling you about. I'm going to somehow or other, what I need to do is to define a difference between two nearly identical triangles, or shapes of triangles. And let's stop worrying about the dilatations, because it's just a few more words, which doesn't really affect the essence of the matter. I'm going to try and bring these incongruent triangles into the position where they are most nearly overlap. Congruence, perfect overlap, is the basis of Euclidean geometry. Let's say that's the position where they are most closely, best matched, closest to being overlapping. And there's going to be a measure to define when they are. I'll show it you precisely in a moment. Then I've got this distance here between particle 1 in that triangle and that one there, this distance here and this distance here. Now, this business of bringing these two triangles together so that they are closest as possible to overlap is background independent. It is not affected by where I walk around in this room. I will get exactly the same relative position of the two triangles wherever I do this. It is background independent in space. It is also independent of any notion of time. Time does not exist in this picture. It is always derived from things that you can see and get hold of. And it doesn't matter when I do this. It's exactly the same now as when I first showed you the triangles in that position a minute or so ago. And by a minute or so ago, I mean that the structure of the world, the shape of the universe has changed somewhat. And that's what I mean by a minute or two ago. By the way, when should I stop? Sorry. Chair, please. What time should I stop this talk? I started at 20 past. I should stop for questions at 12, I mean. Correct? In 20 minutes' time. I'm just about on course, I think. Good, great. Thank you. So let me show you, if I can, the precise quantity to do it with. Here is the basis of everything. Now, the wonderful thing about geometry and those ways of representing it is that it gives me a higher level of geometry. I started off with those surveyors in Egypt discovering geometry on the surface of Egypt. But now I discover geometry in shape space at a higher level. This is a 3n minus 7 dimensional shape space. It's a 2-dimensional space here, but if I've got a lot of particles, it's a highly dimensional space. But up there in the fibre bundle, where all those fibres up there, there's a metric defined up there, which has come because all of this is derived from Euclidean geometry in 3-dimensional space. I can lift it up into the fibre bundle and exploit it there. And you see this here, in the way I've explained, it's enabled me to define a distance between triangles. We started off with defining distance between points in Egypt. Now we're defining distances between two triangles, And at the end of all of this, we'll be defining distances between two complete shapes of the universe that are nearly the same but slightly different. And all that will be done with geometry, which is what holds together the individual configuration. It's Euclidean geometry which is defining my triangles. So that's what we're going to do. And you can see how this comes here. This is where the geometry at the higher level comes in. It's down here. I'm going to do this actually something that is scale invariant. So first of all, I place my two triangles in an arbitrary position relative to each other. That gives me a delta x, and a delta x. So, therefore, I then consider this quantity here. I make the scalar product of that each delta x with itself, weight it with the mass. This is length squared in terms of dimension. I want to have something which is dimensionless, because that's all that counts in reality. So I multiply it by something which is a function on shape space, which must have length to the minus 2 dimensions, and this has no overall length dimension, it's dimensionless. The masses I can always take out and divide by a suitable part of the total mass to make the whole thing dimensionless. So, and then there's a square root because I want a geodesic principle. And the way to get rid of time once and for all is just to put a square root into your action. That's what gets rid of time, is putting that square root in. And then I move the triangles around. Here's an arbitrary position of a triangle. I move them into the best matched position. This means that I'm seeking the minimum of this quantity. It's positive definite. There is a unique minimum which I can find that way. So this is where that comes in. And this is where I have lifted geometry in three-dimensional space up into the multi-dimensional configuration space. And these are those fibers. This is all the different ways of representing one triangle, and this is all the different ways of representing the other. There is that metric on the high-dimensional configuration space, and what best matching is doing is actually picking up the orthogonal separation between the two. So that's what is happening. And then we're away. We've got it. We've got our variational principle. We've got a unique evolution. And out of this, you get a theory where it's just one shape following another. And by the way, this is completely time symmetric. And I think we really should get out of this business of talking about initial conditions. There are no initial conditions in this story. The shapes go on forever. It's completely asymmetrical. All that is happening is that the law that is governing the evolution of the shapes encodes information at any one point and processes it and changes it into a different form. So you have initial information which is the initial, but at any point along that curve you can take a shape and a neighbouring one, and essentially what has happened is that the law of evolution has just transferred information at one point on the evolution curve to another point. So that it's really, the information is encoded, it's a point in phase space. It's the point and the direction in which the system is going in its configuration space. So I would like to get away from this thinking about initial conditions. It's not initial conditions, it's a point in phase space anywhere on the curve that it passes through. So that's it there. Now let's just look at what happens when you do this. I'll go straight on to this thing here. This is how the inertial frames of reference and time emerge from such a procedure. This is an action principle. You have here the key things of this action principle are, first of all, it's got the square root. E is a constant, which later you can identify, if you like, with the Newtonian total energy, but I would much prefer it to be seen as just a constant that you can add to a potential, and this is, you can take this to be the Newtonian gravitational potential. And then T is a kinetic term, but it's not, it's nearly the Newtonian kinetic energy, but it's not quite, because it's divided by lambda, where lambda is a completely arbitrary parameter on the curve in shape space that I'm thinking of. And I'm going to already suppose that I've already found these best matched displacements of the thing. So I'm going to put into the action just these best matched differences. Now I could take that lambda away completely. This is what you say, it's
reparametrization in there, it's completely independent of the parameter. It's timeless in that sense there. So this is the key thing there. You then find the Euler-Lagrange equations that correspond to it, and you get this pretty unpleasant looking set of equations here with this bizarre looking square root there. But it cries out to be simplified. Lambda is completely arbitrary, and this means that T is completely arbitrary. That is fixed, so to speak, as a universal constant of nature. By the way, it's just like the cosmological constant in general relativity, and V is this quantity which is defined on the configuration space or shape space, and you can always choose lambda to make T have an arbitrary value. So you can always make T to have that value. And now let's call that special lambda T, and then you get Newton's second law emerges. But there are two differences. Time has emerged, it wasn't put in the initial kinematics, and secondly, I get the best matched positions of these things there. Now what this means, I'm not going to go through it exactly. What it means is that when I bring the triangles into the best matched position, effectively what I'm doing is bringing the centres of mass to coincidence, and I'm reducing the net rotation to the smallest value it can have, or to zero. And that means that what I'm actually picking up for the complete universe is that it's in its centre of mass frame, that centre of mass is at rest. That's nothing significant because of Galilean relativity, but what is relevant is that the total angular momentum of the universe must be exactly zero. And that's a prediction that Newtonian dynamics cannot make. But there's then nothing to stop subsystems of the universe having any momentum and any value of the angular momentum. And moreover, we can pick up the inertial frame of reference. The inertial frame of reference, just as Machs said it is determined by the universe in its totality, which must have zero angular momentum. And you pick up Newtonian kinematics in its entirety for subsystems. It's only required that the universe, the angular momenta of each subsystem, if you add them all up, must be zero. And that's, of course, more or less what we see when we look out at the universe. We see lots of galaxies, spiral galaxies and clusters of galaxies with angular momentum in them, but there seems to be no trace at all of an overall rotation of the universe. So that seems to be okay from that point of view. Right, let me press on and see if I can get to the end more or less. Now I want to say how time emerges. It's very illuminating just to rewrite this explicitly in this form here. This is the increment of that distinguished time, and you see that it's a very completely holistic expression. You take all of those best matched displacements, you divide it by this quantity here, and you get a completely explicit expression for this time in terms of everything that's happening in the universe. So this is the perfect implementation of what Machs said. It is utterly impossible to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive from the changes of things. And so time is a distillation of all the changes in the universe, and it's doubly holistic. You have to use the best matched displacements to get it, and you have to take them all into account. So this is a completely holistic view of the universe, and it's suggesting that you cannot properly understand what is happening here in this room, ultimately, unless you take into account the whole universe. And underlying all of this, this will work if the universe is a closed dynamical system. And Einstein said, it is only in this case that you can close the circle of cause and effect. I think that's a powerful argument for considering things in that way. I better press on. This is just a picture of how Newtonian space-time emerges in this picture, that you start with an initial triangle, you put the next one in the best matched position relative to it, and so on all the way up, and then you put the vertical separation in terms of this emergent dt that appears. So that's exactly how you get Newtonian space-time, and there's going to be, and I won't possibly have time to go through it all, but there's an exactly analogous way, but vastly sophisticated, how you can build up space-time from this, where you have just space-like hypersurfaces, or three geometries, or even
conformal three geometries, and I'll get on to what I mean by that, where you do an immensely more sophisticated best matching process. But you can entirely build up space-time by a similar process in this way. And I'll just give you some hint of how that is done. So let me just go on. Let me just remind you of some key dates in the history of geometry. In 1854, Riemann introduced the idea of three geometry which has curvature in it. He did it by means of a three-metric. Now, it's very interesting if you read Riemann's paper. He says absolutely explicitly, to measure a length, I have to put my measuring rod next to the interval that is going to be measured. But then he goes on to say, nevertheless, despite this fact, I'm going to assume that it is meaningful to say that my hands, which are separated, have the same length. This is very suspicious. It's just like whether you can define simultaneity in Andromeda as being the same as it is here. What real evidence is there for that? And this was not picked up until 1918 in a slightly different form by Hermann Weyl. The next interesting stage was in 1870 when Clifford conjectured that when my hands are moving around, it's just regions of higher curvature moving relative to each other. He had the idea of dynamical geometry, but it's three-dimensional geometry which is changing dynamically. So then in 1872 and 1883, Mach insists very firmly that all motion is relative. And then Poincaré in 1902 comes up with what I regard as the very precise way to define Mach's principle. And now I'm going to indulge in a little bit of counterfactual history and suppose that Weyl's insight that there was something not quite right with Riemannian geometry that came in 1918 had occurred before Einstein discovered general relativity. And Einstein himself said general relativity should have been discovered 50 years later and after quantum mechanics had been discovered. Think about how different things would have been then. So that could have been what happened. So I'm going to conjecture that Weyl's insight, which came remarkably late considering how clear Riemann had been about the assumption he was making, had come before, and Mach and Poincaré and Weyl had got together to make a theory of dynamics of geometry where only angles count. So what this is saying, the assumption I'm making, is that the bedrock of science is angles and that distance is a gauge quantity. There is no real distance out there. And in fact, when we look out, we actually basically see angles. When we open our eyes at night, we see the celestial sphere. We see angles between stars. The whole of the discovery of the laws of planetary motion, everything was based on measurement of angles. Nothing else went into it. So my conjecture is not only does time not exist, but at the fundamental level, distance does not exist. It's just purely in angles. And let me just very hastily give you just an overview of the things. So a Riemannian three-metric, it's a 3x3 matrix, which gives you dimensionful lengths. Very fishy, distrust them. And so everybody is taught about it. This is at the centre of attention when you learn Riemannian geometry, but it's fishy because it's dimensional. But it determines cosines of angles, which is kosher. This is dimensions, what you get out there. So a Riemannian three-metric has 3 bits of coordinate information. That's diffeomorphisms. You can change that by diffeomorphism, three-dimensional diffeomorphisms. There's 1 scale bit of information. That's just as suspect. And then there's 2 angle data, and that's reality. Okay? So that's what you have there. And superspace is the concept that John Wheeler introduced. It's essentially, so Riem is the space of all Riemannian three-metrics defined on a 3-manifold that is closed without boundary, and any 2 three-metrics that can be carried into each other by a diffeomorphism represent the same 3 geometry. That is superspace. That's the analogue, not of shape space, but of what I call the relative configuration space before I start thinking about dilatations and changing the scale. And there's a way of generating 3-dimensional diffeomorphisms, which I don't have time to go into. Now, much more interesting now is conformal transformations.
A full conformal transformation is obtained by multiplying a 3-metric by a position-dependent function. Purely for mathematical convenience, you take 4 times a positive function of position. And I'm not going to go into the details of whether you restrict it very slightly, because I want to go straight on to the analogue of shape space in this picture here. So now, conformal superspace. There are 2 fundamental groups that come into this. There's the 3-dimensional diffeomorphisms, which is analogous to moving my 2 triangles relative to each other, and then there's the 3-dimensional conformal transformations, and that's analogous at essentially what you have in conformal geometry is the Euclidean symmetry group at each space point. Here, I can only change the size of the complete triangle relative to the other one. But in Romanian geometry, essentially, I can have a triangle at each space point. And so what I'm doing is changing the scale at each space point. And this leads to an immense richness, which is what I believe is really underlying general relativity, and puts it in a totally different perspective when you look at it from this way. So I call the combination of those 2 groups, the 3-dimensional diffeomorphism group and the 3-dimensional conformal transformations, the geometrical group. It absolutely cries out to be the basis of the dynamics of the world. And by the way, matter can go into this story in a wonderfully simple way, and I don't have time to go into that. But then, so conformal superspace, which is the shape space of dynamical geometry, is Riem, the space of all Riemannian 3 metrics, quotiented by this geometrical group, which is the combination of the 2. And so then so this is how it looks in terms of fibre bundles. You have superspace where you're only quotienting by the diffeomorphisms. This is geometric dynamics, which dominated the attempts to create a quantum theory of gravity in the canonical approach from the late 1950s through to today. That's the canonical approach to quantum gravity. And then if you quotient once more, you get to conformal superspace, which is, each point here is a shape of the universe, a dimensionless shape of the universe. And you can add matter fields to it, as I say, without difficulty, and it's all very nice. So what comes out of this, I'm not going to go through any of the details because I've got just precisely 1 minute left. Apologies for going through this. I had rather longer and more preparation in Canada last week. You get, out of this emerges, for a closed universe, a very special form of Einstein's space-time. You get, on the right, you get space-time as it is in Einstein's theory, exactly, but in a uniquely distinguished foliation, which is called constant mean extrinsic curvature. In 4-dimensional space-time, it's exactly analogous to soap bubbles in 3 dimensions. And look how beautiful they are. Soap bubbles have very special mathematical properties, and so do surfaces of constant mean curvature in 4-dimensional space-time. Let me mention that the whole of numerical relativity now, which is a major industry, relies upon surfaces of constant mean curvature. There is no known way to generate initial data for general relativity that does not essentially rely on these surfaces. This was the great discovery made by York, how to solve the initial value problem. Well, Lichnerowicz started it in 1944. York perfected it in 1971-72 with the help of my decade more collaborator Nilo Murukhu from Cork in Ireland. And so you get, and this comes out of the theory with utter necessity. You cannot escape it. In a spatially closed universe treated in this way, you get a uniquely defined notion of simultaneity. Very ironic. Interestingly, when York did his work back 40 years ago, Wheeler conjectured that general relativity might undermine the relativity principle, the relativity of simultaneity, from within itself because of its inherent mathematical structure. And I now feel very confident, I'll not quite take poison on it yet, but I'll take a bet on it that Wheeler was right. And it's a very, very beautiful mathematical structure that is sitting inside general relativity in that way there. So I think that's really all I've got time to say. I'm sorry it was very breathless and rushed, but I'm here to answer questions at least until the end of tomorrow. Thank you very much indeed.
Thank you very much for your extremely interesting lecture. You were hard by all, so I expect now a debate. Professor Jaworowski.
Yes, in your example of two triangles, I'm not sure if I understand what you mean by best matching.
Thank you. I mean Euclidean geometry as taught by Euclid, the basis of it is congruence. You say that two figures are identical if by translations and rotations I can bring them to perfect overlap. But my triangles are incongruent. And this is what happens when you pass from geometry to dynamics. Newton was very aware of this, that the figures now change. In geometry is about unchanging figures. Dynamics is about changing figures. So what I'm suggesting is that dynamics is based on the least possible change you can make to that underlying principle of geometry, that it's based on exact congruence. It cannot be because the shape of the universe is changing. So what I mean by best matching is try to bring my two triangles to the best overlap. Here they clearly are way, way not in overlap. That's much better. That's much better in overlap. But that's even better, and that's even better. And there is a unique position where they are as close as you can get, in that you can minimize a well-defined quantity. That quantity is not absolutely uniquely defined, but it's pretty nearly, it's very restricted in what you're allowed to use as the measure of how different the two triangles are. So that's why I call it best matching.
So you don't claim that any two triangles have that a position of them, that you don't claim the uniqueness of the position of best match.
Once I've defined the quantity that I'm going to call to characterize the measure of incongruence, what you need is a measure of incongruence which only depends upon the shapes of the triangle. That measure of incongruence is not uniquely defined. It gets incredibly close to being uniquely defined in the dynamics of geometry. In fact, it may be. We're quite close to, we're very, very close. At the most, there's a one-parameter freedom. It's due, George, how familiar are you with that mysterious parameter in the DeWitt supermetric? The little lambda that occurs in the... Anyway, there's a very interesting... In the dynamics of geometry, the scale factor that is associated with the expansion of the universe has negative kinetic energy. It's completely unique to geometry, that no other field, anywhere has negative kinetic energy associated with it. The kinetic energy that is conventionally associated with the expansion of the universe has negative kinetic energy, and there's a very precise value that it has. Now, I think that there's a one-parameter freedom, which is now much in discussion with something called Hojava-Lifshitz gravity. It's now actually a topic being investigated. But there's a lot of indications that one undetermined parameter should have one unique value, which is 1. And so I suspect that we will be able to establish that when you try and best match geometry, conformal geometry, the incongruence measure is unique, I suspect.
If you just simplify the situation by looking at segments rather than triangles, or pairs of points, then best matching would mean what?
Sorry, what do you mean by segments? Oh, you mean the size?
Just the size?
Oh, no, that's with respect to your loss. This is all about treating the universe as a complete entity. By the way, perhaps I could just add one thing I would have needed another half an hour about that. What I'm saying, what I would just like to, the punchline, is that when you are thinking about a spatially closed universe, the key thing is actually that unique notion of simultaneity and best matching that's underlying it, and the general covariance that you use in Einstein's general relativity, these other foliations of space-time which are not constantly in curvature, is exactly analogous to going to non-inertial frames of reference in Newtonian mechanics. The heart of Newtonian mechanics, the essence of Newtonian mechanics, is what unfolds in the inertial frame of reference. So it's wrong in the case of a closed universe to regard general covariance in four-dimensional space-time as something fundamental. It is as trivial as going to a non-inertial frame of reference in Newtonian mechanics. However, in the case of an infinite universe, it's exactly the same in Newtonian mechanics and in general relativity. There is no way of picking up a unique inertial frame of reference. Already in Newtonian mechanics, this was recognized 100 years ago, that the local inertial frames of reference, they can be in free fall. So you can pick one up locally, but it can be in free fall. There's no way in an infinite universe that you can pick that up, and the same goes in general relativity. So in an infinite universe, the symmetry group that you do have to think of is, I believe, general covariance, general diffeomorphism invariance in four dimensions, and it's utterly different from the one that's appropriate for a closed universe.
And by infinite, you mean non-compact?
I mean non-compact, yes. Yes.
You compared closed universes with flat geometry. With the flat geometry, I understand.
No. It can be. I mean, it can go. It could be hyperbolic. It could be.
So this was my question. So the problem is similar for open universes of negative curvature as well.
Yes, that's a completely different situation. In that case, there will always be fluctuations, and there will be no. In that case, I do not think there will be any uniquely defined configuration as to the way that foliation in the way that there is in the closed. By the way, this could be of great interest, I think, for cosmology if we conjecture that the universe is spatially closed, because then I would think very strongly that CMC foliation, constant mean curvature foliation, is the way in which one should think about cosmology.
Julian, could we go back to about slide number 3, something like that, where you define your best fitting, I think it was. It was about slide number 3.
Got there. No, one more. No?
Yeah, that's right. What I can't understand, this is a best fitting of shapes, right?
That is going to be the best fitting of shapes.
Well,
I can't show in two dimensions because I can't show expansion.
That's not my question. So if it's a question of shapes, why is there a function called mass in there? What's that mass doing in there? Mass has got nothing to do with shape.
You're quite right, George. Thank you for bringing it up. First of all, what only counts is actually mass ratios, and you have to put them into. I would say this is a defect of a point-particle ontology. There are no masses when you get to geometry. So this is a crutch at this stage, George, where we have to talk about masses as well. But when we get onto geometry, they aren't in there.
And then what's W?
W is it's like a potential. It's a function on shape space. And there is actually a very, very interesting quantity. The whole of the n-body problem is not determined by the Newtonian gravitational potential, but by something which is called the scale-invariant gravitational potential.
Well, somehow you've put Newtonian theory in there, because on the right it says W goes as the inverse of the square of the distance, or something like that.
No, but W goes as 1 upon the length in Newtonian theory. This has got to go as 1 upon the length to the minus 2. It's another power of the length that has to be in the denominator. Yeah, we can talk about it afterwards, George.
And last question.
Yes, I have the following question. You've mentioned that your approach, the conformal structures are the most basic, right? As you look through, I mean, we know altogether that today the spatio-temporal description seems to be in many ways an emergent description, and we're looking for more basic structures. As you yourself said, that probably the conformal structures are the more fundamental, are what is physically real. But are there, like, for example, I'm kind of trying to look at different programs of, for example, quantizing gravity, when you're invoking also different structures which could replace spatio-temporal description at the fundamental level. So, what really convinces you that the conformal structures are the? I'm trying to distinguish from different possible proposals of going to more fundamental structures, that this is just the conformal structures that are the most basic. I know that Roger Penrose also is very much interested in these, and he pays also a lot of attention to what conformal structures are. So why is it that actually the shape is so fundamental? Because, I mean, we come across different proposals for fundamental structures, and how is it that it's just the conformal structures are what is physically real?
Well, first of all theoretical work is based on a hypothesis. You have to put something in to get something out. I am seeking at the moment what I think is the minimum that one needs to put in. And I would ask, it seems to me it's not possible to do theoretical science without at some stage putting in a notion of quantity. So what is the minimum quantity that goes in? And this leads me to say that it has, I suspect it has to be angles. That you can get rid of everything else. If you throw out too much more, I have to say rather sceptical of approaches which say we start from some discrete set. I think this is possibly throwing out too much. King Lear said to Cordelia, "Speak again, nothing will come of nothing." And I would say not much will come of not much, which is why I want to keep at least the angles in the thing there. Now, interestingly, if you look now today, Roger Penrose's spin networks, which he introduced about 40 years ago, are playing a central role in loop quantum gravity. And if you go back to Roger's paper where he introduces it, he says with great confidence that the foundation of geometry must be combinatorial and discrete. There's no other thing there. He's very categorical about that. And a few years ago, I asked Roger if he still stood to that view. He said, well, in the intervening years, I've become rather impressed by the power of complex analysis. And I would say this characterizes my feeling as well. I think it's premature to throw these things, the continuum. It seems to me the continuum is one of the great achievements of the human mind. So if the human mind can work it out, and the human mind is part of the universe, I suspect the universe is using it as well. And so I'm a little bit doubtful about going to the discrete. People invoke Riemann because Riemann twice talks about whether space is discrete. But I think really if you look at the whole thrust, not only of his 1854 paper, but all of Riemann's work, it's really deeply rooted in the continuum.